Hello and welcome to this video presentation about our work on simplified recursion units for the Maxlog map, which will tackle the complexity reduction of the BCJR decoding algorithm with an application to turbo decoding. This work was originally presented at the International Symposium on Topics in Coding in 2021 and has been re-recorded with some additional context. Let's begin with some introduction and background. As seen in this figure, turbocodes are defined by the parallel concatenation of two convolutional encoders separated by a permutation function. They are shown to perform close to the channel capacity limits defined by Shannon and were adopted in many standards such as the third and fourth generations of mobile communications, in addition to some of the digital video broadcasting standards. These codes are decoded iteratively by the well-known Maxlog map algorithm. The turbo decoders have a main advantage over other forward error correcting codes thanks to their highly flexible architecture. The latest implementations have shown that turbo decoders can achieve a throughput of many hundred of gigabits per second while preserving all its flexible properties. And while there have been significant advances in terms of achievable throughput recently, the evolution of today's network systems imposes demands not met by the current state of the art. As one example, ultra-high throughput communications are required for the wireless backhaul link, where large frame sizes are considered and data rates in the terabit per second range are expected for systems beyond 5G. On the other hand, for the control link and some scenarios such as the massive machine type communications, short frame sizes are considered and very low latency communications are required. Existing techniques based on the Maxlog map cannot respond to these demands due to its recursive calculation process and the high number of redundant computations. To that end, defining new techniques to achieve the requirements of the new generation networks is a must. To illustrate this point, let's have a closer look at the Maxlog map algorithm, which aims at decoding over the code trellis by selecting the most reliable transition for each bit at each position. Three processes define this algorithm. The first one is the recursive calculation of the forward state matrix alpha. In the example, to calculate the alpha value at position i+1 for state 0, which stands for the probability of being in the trellis state 0 at this position, we have to select the maximum value between alpha i0 and the corresponding transition branch metric and the alpha i1 with its corresponding branch metric. In general, to calculate the forward metric at position i+1 for any state st, we compare the forward state metric and the branch metric of the two transitions that converge to st at position i+1. The same calculations are applied for the second recursive process, which is the calculation of the backward state metric beta. Here, to calculate the beta at position I and state 0, we should select the maximum between the two transitions that diverge from 0 at position I. And the same goes for all states. The final process is the soft output calculation. Here, we select the best transitions labeled by the systematic bit 0 and the best transition labeled by the systematic bit 1. This algorithm operates recursively and calculates the extrinsic information at every position. These extrinsic values are exchanged with the second component decoder to enhance its decoding capability. To meet the requirements of next-generation wireless communication systems, achieving very high throughputs of several hundred gigabits per second towards terabits per second, a highly pipelined decoder architecture is needed. A common technique to reduce the state metric memory in the decoder pipeline is the parallel processing of several trellis steps at the same time. Processing at a higher radix is particularly useful for fully pipelined turbo decoders, but impractical for higher radix orders with the Maxlog map algorithm due to the long critical path and high area consumption of its computational units, which perform a high number of redundant operations. In this context, different decoding variants have addressed the complexity reduction of the Maxlog map. Recently, the local-SOVA decoding algorithm was defined, reducing the computational complexity of particularly the soft output computation with a remarkable percentage without penalizing the error correcting performance. But what are the differences between the MaxLogMap and the local-SOVA? As stated before, the MaxLogMap algorithm is limited due to its serial nature and the high number of redundant calculations. On the other hand, the local-SOVA can decode on paths through the trellis. These paths are defined as a tuple of the path metric, the corresponding hard decisions denoted by the vector u through the path, and their corresponding reliability candidate values L. A merge operation is defined to select the best path metric with its corresponding hard decision bits and to update the extrinsic candidate values. This update is done with the Hagenauer rule or the Bataille rule, depending on the equivalence or not of the hard decisions of the corresponding competing paths. Note that to more reduce the complexity, the Hagenauer's rule can be imposed as the only update rule on different layers of the algorithm, as we will see later. The local-SOVA algorithm can then be summarized like this. The path merges happen in two phases. First, all paths ending in the same states are merged together in the ACS phase. These merges resemble the calculation of the forward metrics, which is why here we additionally calculate the backward metrics identical to the MaxLogMap. In the second phase, the SOU phase, we add the backward metrics to the path metrics and merge the paths arriving to this phase to get the ML path, including the hard decisions and the extrinsic LLRs, and merge the paths arriving to this phase to get the maximum likelihood path, including the hard decisions and extrinsic LLRs. With a bit of reordering of the merge operations, some redundant operations can be avoided, in particular for the radix 4 and higher case compared to the MaxLogMap. However, the merge operation in the local-SOVA uses Bataille's rule for merges of paths with identical hard decision. While avoidable for radix 2, higher radix orders may require the use of Bataille's rule in the ACS phase. This is illustrated here in the example on the left for the merge of 4 paths in the recursion unit corresponding to the radix 4 case. You can see that the paths are numbered according to the hard decisions that they carry, illustrated in red. In blue, the candidate extrinsic values are shown to be initialized with infinity and then updated with Hagenauer's and Bataille's rule. In the first merges of P0, P1 and P2, P3 respectively, the Hagenauer's rule can be used for updating the extrinsic candidate values for the second hard decisions, which are different, while the Bataille's rule for the first bits, which are equal, can be avoided since the extrinsic candidates are all infinity. In the second step, on the other hand, Bataille's rule cannot be avoided and needs to be employed for the reliability update of the first hard decision. While the Bataille's rule allows to get an accurate reliability value equivalent to the MaxLogMap, the necessary addition lies in the critical path of the ACS operation, which makes it even worse for nested Bataille's rules for higher radix orders. To avoid the use of Bataille's rule in the ACS unit without the loss of accuracy of the reliability value, we proposed in related work to save the challenging path metric as opposed to the delta between the paths. This allows to regenerate the full reliability value in the beginning of the SOU phase and has no impact on the error correcting performance. Since the computation of the delta between path metric of the winning path and the memorized competing path can be hidden in the pipeline of the soft output unit, which computes the SOU phase, the critical path is reduced compared to a naive implementation of the local-SOVA. Compared to the MaxLogMap, however, a penalty of 20 to 30% in terms of area is incurred in the ACS unit. Luckily, as we will see later, this increase is outweighed by the savings in the SOU. There, also we want to avoid the use of Bataille's rule as much as possible. And in the original publication of the local-SOVA in the IEEE Transactions on Communications, it was already suggested to simply replace the Bataille's rule with the simpler Hagenauer rule altogether. Since the consequence is a 0.3 dB loss in error correcting performance, we proposed to instead replace the Bataille's rule with the following update rule. use the previous extrinsic candidate or L value of the winning path or the best contending value among all contenders. Explicitly considering all contenders to the winning hard decisions helps mitigating a loss in error correcting performance. This complexity reduction can now be applied either to the whole merge tree in the SOU or to subtrees, allowing a trade-off between implementation complexity and error correcting performance. And as we see here in the bit error rate simulation results for 3 LTE turbo codes for rate 1/3 and BPSK modulation, the single use of Bataille's rule for the local-SOVA 2 brings only a negligible performance loss, while local-SOVA 1 loses about 0.2 dB at bit error rate 10 to the -6. We implemented soft output and ACS unit in VHDL and placed and routed them for 22nm technology alongside their MaxLogMap counterparts with identical quantization for fair comparison. I want to highlight the main takeaways. First, as predicted in the original local-SOVA paper, the area consumption for the radix 2 case is almost identical for both algorithms. For the radix 4 case, the additional overhead due to the needed lookup tables accounts for a 20% area increase in the ACSU, but on the other hand, the area for the soft output unit is halved. This trend is even more pronounced for the radix 8 case, where a 30% increase in the ACSU stands against a saving of almost 75% in the soft output unit. To summarize this introductory part, the local-SOVA highly reduces the complexity of the soft output computation compared to the MaxLogMap, but does not reduce the number or complexity of the ACS unit. Which brings me to the two new decoding algorithms, which are variants of the local-SOVA, which we proposed in order to reduce the complexity of the recursive units previously not addressed in the local-SOVA decoding algorithm. As we have seen, the local-SOVA decoding algorithm was shown to highly reduce the complexity of the soft output computation, paving the way for very high throughput implementations. However, the serial nature of the BCJR decoder was not addressed, and therefore the complexity of the ACS was not reduced. A first, seemingly trivial solution is to consider very high radix orders. For example, if W is the size of a decoded subtrellis, a radix order of 2 to the power of W over 2 would be efficient in order to reduce the number of the ACS units. Here, recursive calculations are performed to calculate the forward metric at the middle of the subtrellis. And the same is performed for the backward recursion. After these calculations, one local-SOVA dual-sided soft output unit is sufficient to calculate all extrinsic outputs of the subtrellis. However, for practical decoding, where W is in the order of 32 or 64 bits, these high-radix ACS units become impractical for hardware implementations. To this end, we limited this work to the case of radix 4 ACS units, where the forward metric is calculated by steps of 2 from the start of a subtrellis to its middle, and the backward metric is calculated from the end of a subtrellis to its middle. When meeting in the middle, the forward alpha and the backward beta recursions are known, and therefore a new metric is defined as the sum of alpha plus beta. This metric is called tau and can be used as input for the soft output unit. From the middle point, two possible solutions can arise: reducing the complexity of the ACS units performed after the meet in the middle, or reducing the number of performed ACS units by directly applying a global soft output unit at the middle. In this last case, ACS units should be adapted to perform updates throughout the subtrellis. In the first case, we propose to limit the complexity of the ACS units performed after the meet in the middle. To be able to do that, some additional metrics should be memorized when performing the recursive calculations before the meet in the middle. For example, when calculating the forward recursion at position I from position I-2, 4 connections are considered for state J, where we are working with a radix 4 trellis. Here, only one connection would be the winning path that defines the value of the alpha at position I. In order to apply our proposal, the values of delta should be memorized. These values define the difference between the winning path and the losing ones, as shown here with the example of delta 2 between the path from state 2 and the winning path, delta 1 between the path from state 1 and the winning path, and so on. The same goes for the backward recursion. When arriving to the middle, tau is calculated and the values of deltas are memorized. We propose to estimate the values of tau at position I from position I plus 2 at the left side of the subtrellis and from I minus 2 at the right side of the subtrellis. Taking the example of the left side of the subtrellis, if the considered state j is at the starting point of only one winning path, the value of tau is directly copied from position I plus 2. On the other hand, if j is the starting point of more than one winning path, the maximum value between the corresponding taus is considered. And finally, if no winning paths emerge from j, the maximum value between tau I plus 2 is corrected with the corresponding correction factor delta. The same applies on the right side of the subtrellis. Having the values of tau at each position of the subtrellis, a local-SOVA soft output unit is applied at each position to output the extrinsic values. Applying this algorithm, the error correcting performance can be seen to be slightly affected for different coding rates when compared to naive local-SOVA decoding. In addition, this proposal reduces the complexity of the ACS units by almost 13% in comparison with the local-SOVA. The second proposed algorithm is based on reducing the number of the performed ACS units. Note that we explicitly show here only the case of the forward recursion in this explanation, but the same applies for the backward recursion. When calculating the forward recursion at position k plus 2 from position k, an identified number of previous bits, here defined as nf, is updated respecting the local-SOVA update rules when doing the corresponding merges. These forward calculations and updates are applied until arriving to the middle point of the subtrellis. At this point, the values of beta are obtained in the same manner and the bits at the right side of the subtrellis are also updated. A dual-sided global local-SOVA is applied to output the extrinsic values for all positions. Here, at each merge step in the merge tree of the SOU, an identified number of previous bits are also updated. At the first step of the SOU, this number is identified by NSOU1. At the second step by NSOU2 and finally with NSOU3. After all these updates, the extrinsic value is calculated for all positions. In this algorithm, different configurations can be studied. These configurations differ in the number of updates performed during the recursive calculations and in the SOU unit. In this example, we show the different configurations when considering a decoding window size of 32. The values of n are tested with 4, 8, and 16. Obviously, these different configurations will result in different complexity reductions when compared to the local-SOVA. When a limited number of updates, for example 4, is applied at each step in the example of C1, the number of ACS units is largely reduced when compared to the local-SOVA, here in the order of 37%. On the other hand, small complexity reductions are observed when considering all updates in the SOU and slightly reducing them in the recursive calculation. In all these cases, the number of ACS units is reduced when compared to the local-SOVA, but the most interesting gain remains in the reducing of the latency of the decoding algorithm. By applying this MDS local-SOVA algorithm, the error correcting performance is directly related to the considered configuration. For example, when considering the configuration C1, where only 4 bits are updated at each recursion at the SOU, 1 dB of performance loss is observed. This loss is reduced whenever we consider a configuration with a higher number of updates. In conclusion, we can say that these two new variants which we propose give the designer several trade-offs to balance complexity and error-correcting performance. While the local-SOVA had already previously been shown to allow significant complexity reductions compared to the traditional max-log map, the present work illustrates that with additional modifications to the decoding algorithm, Further reductions in complexity are possible, paving the way for future applications requiring ultra-high data rates and low decoding latencies.